Good afternoon. This podcast is going to focus on the learning target for observing thermal properties of metals and specifically being able to calculate the coefficient of thermal expansion for metals. I'm Miss Mikesell and I'm one of the material science teachers, and I hope this podcast is helpful. So, thermal properties are properties that are presented when a material is heated. Thermal properties are considered physical properties, and they include thermal conductivity, thermal expansion, as well as the heat capacity or specific heat of the material. Today, we're going to look more closely at thermal expansion. Thermal expansion occurs when the temperature rises and molecules move faster, taking up more room. So you can see that in the before picture, before we heat or after we cool, because the heating and cooling process would be reversible, our molecules have less kinetic energy, less vibrational motion. After we heat up a substance or a material, though, those molecules have a greater kinetic energy. They are vibrating at a faster rate, and thus they are going to be expanding or taking up more room. So, our task today is to measure the rate of that expansion, how much expansion occurs within a given temperature change. To do that, we're going to quantify or calculate the coefficient of thermal expansion. That's the amount per degree of expansion divided by the change in temperature. So this is the equation that we're going to be using. This Greek theta symbol is the coefficient of thermal expansion. And to solve for it, we're going to take the delta L, delta means change in, the difference or change in length, divided by the original length times the change in temperature. So this is a nice simple algebraic equation. Again, to solve for the linear coefficient of thermal expansion, we will take the change in length and divide it by the original length multiplied by the change in temperature. Note, since there's two variables in the denominator, you do need to be sure to program your calculator correctly so that it divides by both of these variables. So why do material scientists care about the coefficient of thermal expansion? Why is it important to measure this? And the reason is we use this all the time in industry. If I want an axle to be tightly fitted into a wheel for a car, which certainly as a driver I want, because I don't want to be driving down the road at 70 miles an hour and have my axle fall out of my wheel, then how they do that in industry is they often cool it down using liquid nitrogen. Cooling it down instead of thermally expanding the material would thermally contract the material. That allows them to slide the cold axle into the wheel hub. And as the axle normalizes to room temperature and equalizes, it's now going to be tightly fit into the wheel hub. They can basically get a tolerance that's zero and perfectly seam these two things together by thermally freezing the axle before inserting it and allowing it to insert perfectly into the wheel hub. Another example would be engineers have to calculate thermal expansion when they decide how far apart to set telephone wires and how taut to run those wires when they initially install them. That depends on the climate of a region in many cases, because you have to look at the climate in the winter and how cold it gets versus in the summer how warm it gets. We don't want the electrical wires to get so cold in the winter that they snap, but we also don't want them to expand so much that they sag down to a dangerous level in the summer. A third example, wow, look at those railroad tracks. You would not want to be on a train on an Amtrak when you hit those tracks. That's what's going to cause a derailment, right? So thermal expansion, if the material has not been engineered to have expansion joints, is going to cause a buckling if it expands and changes linear length too much. And so these railroad tracks are a prime example of thermal expansion that they have not accounted for, providing expansion joints and other things. And so you got the buckling or the curvature of the tracks that resulted. I am sure you've probably passed by a sidewalk on a warm summer day in Denver that's buckled and now it looks like a roller coaster for the same reason. So you can see expansion joints have been placed on a lot of bridges, and I bet if you've ever walked over a bridge, you've seen those expansion joints. Engineers use those to protect the bridge from buckling and collapsing due to thermal expansion. All right, take a second in your notes and let's practice this first problem together. On a very cold day at a temperature of negative 12 degrees Celsius, a power line made of aluminum between two support towers measures exactly 150.56 meters. You go out on a hot day at a temperature of 29.5 degrees Celsius and measure the power line to be 150.71 meters. Please calculate the thermal expansion coefficient. So to do that, we're again going to be solving for theta, or the coefficient of thermal expansion. And that means we need to know our delta L, or our change in length. So change in means the difference in length. We're going to always subtract the higher value from the lower value because we just need to know what is the change in length experienced. Doesn't matter if it expanded or contracted. What's the change? So 150.71 minus 150.56 gives us a delta L of 0.15 meters. Then we need to determine what our original length is. So that's the length that the line started at before the temperature change. So that would be 150.56 meters. Finally, we're going to calculate our delta T, or our change in temperature. So our change in temperature is going to be the difference between the initial and final temperature. Again, that's an absolute value. We're looking at how much the temperature changed over the testing time period. So we started at a very cold temperature of negative 12. Envision we warmed up to 0, and then we continue to warm up to 29.5 degrees. So when we calculate our change in temperature, we need to recognize that that temperature, instead of subtracting, it would be minus a negative number, which means addition. And we have a total change in temperature of 42 degrees Celsius. Because again, we went from negative 12 to 0, and then from 0 to 29.5 degrees. Envision that on a number line. So now that we have our three givens, we can simply substitute into the equation to solve. Delta L would be 0.15 meters. Our original length is 150.56 meters, and delta T is 42 degrees Celsius. On your calculator, solve 0.15 meters divided by parentheses 150.56 times 42, close the parentheses. You're grouping both of those values in the denominator, so your calculator divides by both parts. And we should get a thermal expansion coefficient of 2.37 times 10 to the negative fifth per degree Celsius, or 0.0000237. Some people's calculators will express the answer in scientific notation. Make sure to look all the way to the right to see that exponent. Others will put it in standard form as a very small number. Note, meters canceled out. Meters in the top and meters in the bottom canceled out. So our answer is the change in the linear length experienced per every degree Celsius change in temperature. In other words, every time we calculate the thermal expansion coefficient, we should expect the number's going to be very, very small, because for a 1 degree Celsius change in temperature, we're going to have a very tiny change in the linear length. All right, take a second and pause me and try this problem yourself. All right, let's take a second and look at it. Again, we're calculating the coefficient of thermal expansion. You should have found the change in length to be 0.018 meters. The original length would be 50 meters long. And your change in temperature would be the difference between the initial and final temperature, 50 minus 20, or 30 degrees Celsius. When you substitute that into the equation and solve, again, remember to group both values in the denominator, so you're dividing by both, we should get a thermal expansion coefficient of 1.2 times 10 to the negative fifth per degree Celsius, or 0.00012 per degree Celsius. Let's do one more problem. So again, pause me and try this problem yourself, and let's make sure you can do it. In this case, we're taking this problem from a lab data set instead of a word problem. Hopefully you calculated the change in length to be 0.007 meters, the change in temperature to be 50 degrees Celsius, because we were starting at a temperature of 20, we went to 0, and then we went all the way down to negative 30 degrees. So when you subtract a negative, it becomes plus, in other words, a change of 50 degrees Celsius. So now our change in length is 0.007 meters. Our original length is 6 meters, and our change in temperature is 50 degrees Celsius. When you calculate the thermal expansion coefficient, we should get 0.0000233 degrees per 1 degree Celsius. So, can you explain in the lab why the bimetallic strip always curves in the direction that it does? Remember that a bimetallic strip is made of two different metals that have been bonded together. In the case of the illustration shown, it's steel on one side and copper or brass on the other side. So why, after heating, did the bimetallic strip curve in the direction that it did? To answer this question, we need to look at the known thermal expansion coefficients for these two metals. Steel has a thermal expansion coefficient of 11 times 10 to the negative sixth, whereas copper is 17 times 10 to the negative sixth. In other words, copper has a larger change in linear length for every degree Celsius temperature change than steel does, since it has a higher number or higher coefficient there. So a great way to think about this is if you've ever run track or if you've watched a track meet, you know that they have a staggered start for many of the races on the track. And that is because at the curve of a track, you're not running the same distance. You actually are running a greater distance if you're on the outer part of the curve than if you're on the inside of the curve. So thinking about that related to our copper and steel, we should be able to see that copper, because it has a greater thermal expansion coefficient, it has a bigger change in linear length for every degree Celsius of temperature change, needs to be in the outer lane. It needs to always curve so that it stays in the outer lane because it is going to experience a greater expansion than steel does. So essentially, the direction that the bimetallic strip curves can be predicted based on the thermal expansion coefficients of your two metals. The metal that has the higher thermal expansion coefficient will always experience a greater change in linear length and thus will need to curve in the outer lane so that it can cover that extra distance. So let's look at a quick example of why we use bimetallic strips, because they're an extremely important part of material science. They're often used in griddles, irons, thermostats, and ovens. Anytime the temperature fluctuates, the strip can bend in different directions to automatically turn on or off the heat source.
This is just a short little video to show you how a thermostat works with a bimetallic strip. So this would actually be the cover that we would see on top of our thermostat, and the switch that's right here would actually come out the bottom. So the inner workings of the thermostat we have the switch right here that moves back and forth as we want to turn the temperature up and down. We actually have a bimetallic strip around here that's coiled around, and then we have a capsule that has a mercury bubble in it right here. The mercury is a metal, so it will conduct electricity. And when the mercury is in that position, it's going to connect the two wires that are at the end, and it's going to turn on the furnace by closing the circuit. When it's over here, it's not going to do that. So when we want to turn the heat up, that means we turn it this way, and the mercury bubble goes in to connect the circuit. The bimetallic strip will eventually heat up and it will uncoil, and it will eventually turn like this. When it cools down again, it's going to slip back and turn the furnace back on again.